Hello everyone, welcome back on the next video in this series of linear algebra question which are asked in the GATE exam in the previous year. So let's start this video. So now let's solve first question. So here question 1 says in a matrix equation Px equal to Q, and here P is nothing but the coefficient matrix and Q is our vector, unknown vector in this form of our variable x1, x, y and z generally for three unknown, and here q is again the vector. Which one of the following is a necessary condition for existence of at least one solution for the unknown vector x? Okay, here the vector x is unknown. Now they are asking about the necessary condition such that this equation px equal to q, it has at least one solution. Okay, so we have system of equation here, and we have represented in this form px equal to q, and now here this p is our coefficient matrix. So now the for existence of solution, so let's go through four options. Option A says a matrix p must be singular. If this is the case, let's again, if they are saying if this p is singular, that means determinant of this coefficient matrix p is 0, then we are calling it is a singular matrix. So option A says if p is singular, then and then the at least one solution exists. But now here recall that I have discussed in the previous video that if the determinant of any matrix, any coefficient matrix is 0, then there will be a two possibility. One possibility is that there is the no solution for this system. It is the one possibility out of two, and the second one is that there may be a infinite solution. So now these are the two possibility if the determinant is 0. So now here they are asking about the at least one solution. If this is the case for this singular matrix, then we are getting a non-zero, no solution. That means our system is inconsistent. So option A must be wrong. So option A is not correct one. So now let's move to the option B. Option B says matrix P must be square. Now here it is not necessary that here the coefficient matrix P must be square. Here what happens sometimes, either I have more equation than the unknown, or I have less equation than unknown. Then in that particular case, I got this matrix P as a rectangular matrix, not a square matrix, but still I can get the solution. So now again, option B is not also a necessary condition. So now option C says the augmented matrix P formed with the help of this coefficient matrix in this Q must have the same rank as a P. Yes, it is the correct statement, because you may recall that if for the solution of simultaneous equation, the necessary condition is that rank of coefficient matrix is exactly same as the rank of augmented matrix. Now if this condition is going to hold, then and then we are getting the solution. So now option C describes the correct statement about the necessary condition for at least one solution. Now also let check option D. Option D says vector Q must have a non-zero element. Now again it is not the case here, because here the system may be homogeneous or non-homogeneous. If the system is homogeneous, then we are getting here this Q as a zero vector. But now here they are in the option C, they are saying that vector D must have a non-zero element. Now again it may have a zero value. So again option D is not necessary condition to get the at least one solution. Okay, now let's solve question number 2. Question 2 says for a matrix we have P matrix and which has order of 3 cross 3. One of the eigenvalue is -2. Which one of the following is an eigenvector? Okay, so again we have to use the same concept. this ax equal to lambda x, but here we have given the value of lambda here and which is minus 2, but here it not make any difference. We have to do the same procedure. Let's write the matrix A here, 3 minus 2 2. Again, you may recall this matrix is nothing but the upper triangular matrix because all entries above the diagonal are non-zero and below the diagonal are 0. So we are calling it an upper triangular matrix. So now let's multiply this matrix with vector which is given in the option A. So it has value minus 3, 2 and minus 1. So now let's do this multiplication. So what we are getting here, minus 9 minus 4 plus 2, here minus 4 minus 1 and minus 1. So let's further simplify it. So here getting minus 11 minus 5 and minus 1. So now if you try to find out some scalar lambda to represent this vector in this lambda times the initial one, which is this one. So now let's put some unknown lambda here, and here let write the initial vector. Now here the value of lambda in the question is given minus 2. So let's put lambda equal to negative 2 here. So let's multiply this with this vector. If we put lambda is minus 2 here, then here we are getting minus 6, sorry, plus 6, but on the left hand side we have negative 11. So these two elements are not going to equal. Also these two are not going to equal, and the same with this third one. So we can say this equation is not going to satisfy for the lambda, for value of lambda is negative 2 here. In other words, we can say that there is no any such scalar to represent this vector in this form. So we are not getting any scalar for this. So option A must be wrong. Now let's move to the option B. Again, let's write the vector as it is. Sorry, this matrix as it is. Let's multiply it with vector given in the option B, which has value 2 5 0. Again let's do the multiplication. So here 6 minus 10, so minus 4. Now here minus 10, and here again we are getting a 0. So now again let's try to find out some scalar here also to represent this vector in this lambda time initial one, which has value 2 5 and 0. Now again let's select this lambda equal to minus 2 and put it here. So here let's multiply this minus 2 with this vector. So here we are getting minus 4, which is exactly same as this one, and here also we are getting minus 10, which is exactly same as this one, and here the entry will remain as it is because here we have 0. So again the all the entries on the left hand side and right hand side are equal. So we can say this equation is satisfied for lambda equal to minus 2. So now we can say this vector is an eigenvector of this matrix, and it is corresponding to the eigenvalue of negative 2. So we can say option B contains the correct eigenvector for this matrix. So now you may check option C and D, but they isn't satisfying this condition. So the correct eigenvector for this matrix, and particularly for this eigenvalue of negative 2, which is given in the option B. So option B is the right choice. Let's move to the question 3. Okay, now let's solve question number 3. So question 3 says if R, again we have some matrix, and which has also again order of 3 cross 3, then the top row of R inverse. Okay, so they are asking about the top row of the inverse of this matrix. So now first of all, to find the inverse, recall the formula of inverse. Here let's denote as R inverse. So we have to first of all find the determinant of this r, and we have to put in the denominator, and we have to multiply it with adjoint of this matrix. Here it is r. So now first of all we need the determinant to find the adjoint, sorry, to inverse. So let's first find the determinant of this matrix. So now here, so this second element will 0. So again I simply just put it here 0. The third element, I got 6 minus 2. So now let's simplify further. So here I'm getting 5, here 0 already there, and here plus 4. So I have to multiply it with minus, so negative 4. So I have find out the determinant, and which is 1. So now put this value 1 here in the place of this determinant of r. So I can write just simply inverse of this matrix is nothing but this simply the adjoint of this matrix r. And how to find the adjoint? To find the adjoint, to find the adjoint of r, we have to do 3 steps. First step is that find minors of matrix. Now here the matrix is 3 cross 3, so my all minors are in the form of 2 cross 2 matrix. And second, make cofactor matrix from this. And how to make the cofactor matrix is just simply multiply this multiply this determinant of this minus matrix with the this sign factor minus 1 raised to I plus j. And here I and j, it is the particular index of this particular element. Here for this one the I and j have value of 1 and 1 respectively. For this 0, the value of I is still 1, but the value of j is 2 because it is present in this second column. Basically this I and j represent the address of any particular element in this 3 cross 3 matrix. So now in the third step is that take the transpose of matrix, but this matrix which I got from this second step. In other words, I have to take the transpose of this coefficient matrix. So now after taking the transpose, this first column of this matrix cofactor matrix will be my first row in the inverse, and that I have to find in this question. So now I have to find this minors of this column, first column here in the matrix. I have to find the minors of this one, this two, and these two, and I have to make this cofactor with multiplication of this factor, sign factor. And then if I am taking the transpose, then this whole first column will be my first row of this inverse matrix. So now quickly let's find the minor of this first element. So here it has address of a11, so I can write here the minors of this one a11. So simply I have to delete this first column and first row because this entry is present in this first row and first column. So I have to just simply delete this column and this row. So I end up with this 2 cross 2 minor. Let's write it here. So 1 minus 1 3 2. So I have to find the determinant. So here just simply 2 plus 3. So I am getting 5 as a determinant of this minor of this a11. So I just simply write here let's 5. So again I have to find the minors of this element, and here the address of this element is nothing but the which is present in this second row and first column. So I can write a21, and here again let's delete this row and this column. So I end up with this minors of second order 2 minus 1 3 2. So now again let's find the determinant. Again I am getting here plus 3. So now the last minor which is corresponding to this element, and it has an address of third row and first column. So again let's delete this first column and this third row. So I end up with this second, sorry, 2 cross 2 determinant, and let's find the determinant. Here I am getting again the plus 1 as an determinant of this 2 cross 2. So now I have to find the cofactor. So I am denoting as C11, C21 because C stand for the cofactor, and this let's call C31. So what I have to do is just simply multiply this value with I minus I to the power of this sum of these two values. So minus 1 raised to 1 plus 1 because value of I and j are 1 1 here respectively. So minus 1 raised to power 1 plus 1, and I have to multiply it with the determinant of this minus 2 cross 2, and which is 5. So I just simply write it here as positive 5 because here I am getting minus 1 square, so again it will positive, so simply I am getting plus 5. Now let's find the cofactor of this a21. So here I am getting minus 1 raised to third power, so again here I am getting minus sign in the front of this determinant. For this one again minus 1 to the fourth power, and again the power is even, so again I am getting positive 1 as a factor. So just simply my cofactor has value simply positive 1. So now let's form the first row here. So 5 minus 3 and 1. So it is our first row for this inverse, but here remember that the determinant here for this particular case is 1. So we have just simply got the value as the cofactor because the value of determinant is here is 1. So it is the factor scalar 1. So it doesn't make any difference. So now option C contains the correct entry according to this 5 minus 3 and 1. So option C contains the correct first row of inverse matrix. So now in this way you can easily find any element which is required for your inverse matrix. So you have not need to find all R inverse because they are asking about this only top row. So just find the cofactor of this column, and there if we are finding the adjoint, we have to take the transpose, then this whole column will convert it into the first row of inverse matrix. So now we have to just find the minors of this column and then make cofactor and then make this column as row, and it is our answer. Let's move to the next question. Okay, now question 4 says if A has a value of minus 3, 2, minus 1 and 0, and again it is a matrix of 2 cross 2 order, then A satisfy the relation. Okay, so they are asking about the from these four relation which relation is satisfied by this matrix A. So now here you may recall that this question is corresponding to the Cayley-Hamilton theorem because the theorem states that every matrix satisfy its own characteristic equation. So it is the Cayley-Hamilton theorem. Cayley-Hamilton theorem we have to use in this question. And what is the theorem says? Theorem says that every matrix satisfy its own characteristic equation. So now first of all we have to form the characteristic equation for this matrix A here. So let's form here characteristic equation with the help of this determinant A minus lambda I. And you have to equate this determinant equal to 0. So now here let's form the determinant. So here I am getting minus 3 minus lambda, 2 here as it is, minus 1, and here minus lambda, and I have to find the determinant and equate equal to 0. So now what I am getting here is determinant minus lambda here plus 2 equal to 0. So now let's multiply this lambda with this bracket minus lambda with this bracket. So here I am getting plus 3 lambda plus lambda square plus 2 equal to 0. So now it is our characteristic equation for this matrix. So but all the relation are in this form A, and here the A is our matrix. So now let's replace this lambda with this matrix A, because the Cayley-Hamilton theorem say that every matrix, here the matrix is A, satisfy its own characteristic equation. So here we have find out the characteristic equation. So we can say with the help of Cayley-Hamilton theorem, we can write 3a plus a square plus 2I equal to 0, because here we have to put I multiplied with this 2, because here we are replacing this scalar with identity matrix, because this equation are in the form of this matrix. Here A is a matrix. So now look at the option A look like similar, but here they have given in the form of inverse. So now what we have to do is just simply multiply this equation with inverse both the sides. So let's multiply with A inverse. So here what we are getting, 3 A inverse time A plus A inverse time A square plus 2A inverse time I, and here the right hand side we again get 0, because 0 multiplied with inverse again gives me 0. So now here I can reduce this multiplication, inverse multiply with its over matrix. So I can write here 3 times identity matrix plus here I can reduce one power of this square with the help of after multiplication of this inverse. So I can write here simply A, and here 2 A inverse. So now look at the option A. Option A is the exactly same as this one. So now option A has the correct relationship which must this matrix A is satisfied. So option A is the correct answer for this question. Okay, now let's solve question number 5. Question 5 says if A, again we have a same A matrix, then the A to the power 9 equal to what? Okay, so they're asking about the ninth power of A. So now here there are two methods basically, in two more, even there are more than two, but here I am going to discuss the two method. The first one is same, because that we have did in the previous question. We have to first of all we have to find the characteristic equation equal to 0, and then we have to reduce this A power like this, sorry, A to the 9 power like this. So I can represent, sorry, I can write this 9 power as A to the 3 to the 3. So now with the help of this characteristic equation, first of all I have to find this A cube, and then I will cube its whole, and again after successively replacing the value of higher order with the help of this characteristic equation, at the end we find the linear equation for this A to the 9 power in some linear form. So now here this is the first method. Now the second one is, here it take more time. For the second method what we are going to do, we are take the help of eigenvalue. But now we know if any matrix A has eigenvalues lambda, then A to the n has eigenvalue as lambda to the n. So now it is the property of eigenvalue. And now another property is that if the matrix has in this form of this linear equation, then we can replace this A with the eigenvalue. With the help of Cayley-Hamilton theorem, we can replace this matrix A with any particular eigenvalue, here in this case of lambda. So now this I will reduce with 1, because this identity matrix is eigenvalue of 1. Any identity matrix has eigenvalue as 1. So all the identity matrix. Irrespective order, it may have any order, but still its all eigenvalues are unity. So now we have to use this property to solve this problem, because this second method, this one, give the answer very quickly than this one. So now first of all we have to find the eigenvalue. So let's quickly find the eigenvalue. So here again we have to need to form the characteristic equation. So now here I am getting 3 lambda plus lambda square plus 2 equal to 0. So let's write it in this way: lambda square plus 3 lambda plus 2, and you have to equate is equal to 0. So let's find the value of lambda. Let's call it lambda 1 and lambda 2, because this polynomial is with second order, so we are getting two roots. So let's find with this equation: minus b plus or minus under root of delta, and here delta square is b square minus 4ac, and here value of b is 3, so I can reduce it with 9, because I have to square it. B square minus 4ac, so I have to multiply it with 4 with this 2 with this here factor, sorry, scalar 1. So again I am getting here 8 divided by 2a, and here a is again 1, so I can write simply 2 multiplied with 1, which is 2. So now minus 3 plus or minus 1 by 2. So the two eigenvalues for this A matrix has a value of minus 2 and minus 1. So now we have find out the value for this A matrix, but in the question they are asking about the A to the ninth power. So let's find the eigenvalues for A to the 9 matrix. So now what we have to do, we have to just raise this power of this eigenvalue with 9. So I can write 2 to the 9, and here minus 1 to the 9. So here, so in the first case the number is very big, because we have raised the power of this 2 with 9. So now let's move on the second one. If we raise the power of this minus 1 to the 9, then again we are getting minus 1, because power is odd. So simply the one of the eigenvalue of this A to the 9 matrix is minus 1. So now the next step what we have to do is just we have to go through the option, which one of the option gives the eigenvalue as negative 1, because if we put the equal to for this equation on the left hand side A to the 9, then the must this either one of this relation must have give the eigenvalue of minus 1, because A to the 9 has eigenvalue of minus 1. So now let's check for the option A. So let's find the eigenvalue here for this matrix. So I have to just replace this A with this particular eigenvalue, and here it is minus 1. So I can replace this, sorry, I can multiply this 511 with minus 1 plus 510 multiplied with 1, because here the matrix is identity. So I have to replace that identity matrix with its eigenvalue, and all identity matrix has eigenvalue as 1. So simply I have to multiply this 510 with 1. So now if you solve this, I am getting is minus 1. So yes, I am getting the eigenvalue as minus 1 for this A to the 9 from this option A. So option A is the correct relationship that describe this A to the 9 power in this linear form. So now also let of course option B is not the correct one, because the exponential 9 exponential to the 9a, it not make any sense. So option B is not correct one, because we are not getting exponential in from this characteristic equation, because the characteristic equation is always in the form of polynomial. So in the output we are also getting the polynomial in the form of polynomial function. So now this A to the 9 must be in the form of some polynomial, and here this function is not represent polynomial, so option B is not correct one. Now let's check this option C and D also. So now let's again, this is the for option A, let's write it here. So option A gives the eigenvalue as negative 1. So let's move to the option C. If multiple options are giving the minus 1, then I have to go to this second value. But let's check it here what happened for this option C. So now again let's multiply this 154 with minus 1. So I can just simply put 100 minus 54, and I have to add this with 155. So here I am getting plus 1, but the eigenvalue for this a to the 9 which has value of minus 1. So again it is not giving the correct eigenvalue. So option C is not correct one. Option C is not correct one. So the let's check for option D also. So let's put it here again minus 1. So minus 309 plus 104. So again it is not giving minus 1. You can easily see that. So now only the option A satisfying for this minus lambda of minus 1. So option A must be the correct relationship that describe this a to the 9 power in this reduced form. You can still get the same answer with the help of this one. So now let's move with this first method. Here from this up to this all the steps are common. In this first method all the steps are common up to this point to find the characteristic equation. And now let's reduce this this characteristic equation in the matrix form with the help of Cayley-Hamilton theorem. So I can write like this: a square plus 3a plus 2i equal to 0. And now let's bring all these terms except this a square on the other side. So I can write a square equal to minus 3a minus 2i. So now I have find out the a square, so I need a cube. So now let's multiply this equation further by the matrix A. So I can make the left hand side is a cube, and here I am getting 3a square minus 2a. So now again we have to replace this a square with this value. Sorry, I have to again replace this a square with this value. So I have find out a cube, and again I have to cube it. So I am getting the further power, and again I have to reduce with the help of this equation to make the power first, and you still get this same linear equation. So now but this second method is very easy for this MCQ type question, so I recommended this method for this kind of problem. So now let's move to the next question. Okay, now let's solve question number 6. Question 6 says, for which value of x will the given matrix become a singular? Now first of all we need the definition of singular matrix. We need to know the definition of singular matrix. So now for any matrix, let's call it, say, if the determinant of any matrix will be 0, then we are calling this matrix A is singular matrix. And if the determinant has a non-zero value, then we say that A is non-singular matrix. So now it is the basic definition of singular matrix. So they are asking about the value of x for which this matrix will be singular. Simply we have to find the determinant and equate equal to 0, and simply from that we can find the value of unknown x here. So now let's form the determinant: 8 x 0 4 0 2 12 6 and 0. Okay, so now we have to equate this determinant equal to 0, because the condition is given in the question, stated in the question, that matrix must will become singular. So now let's find the determinant. So here let's expand with respect to this first row. So here 8 multiply with 0, because from this second order minus I am getting 0. So now minus x multiplied with this second order minus. So let's find the determinant of this minus. So here I am getting minus 24 plus the third entry has multiplication with 0. So again 0. Now and we have to equate this with equal to 0. So now one can say 24x equal to, sorry, here the entry is 6, I consider it as 0, sorry for that. here the value is 6, but I have put it 0. So so what I am getting here, the multiplied with 8, here the minus of this 2 cross 2, I am getting minus 12. So let's make the correction here. So here I can write plus this minus 12 times 8, and we have to equate equal to 0. So let's solve for the x. So I can write like plus multiply with 8. So I can factor out here 2 and again here 4. So I can say the value of x here in this case is 4. If I put the here 4 in the place of x, then the determinant of this matrix will be 0 and it's become a singular matrix. So option B is the correct one. Okay, now let's solve question 7. So question 7 says consider the matrices. We have X matrix which has order of 4 cross 3, and we have a Y matrix with the order of 4 cross 3, and we have a P matrix with the order of 2 cross 3. So they're asking about the order of this matrix. We have some long equation in this form of transpose and inverse and again transpose of again transpose will be what? So they're asking about the order of this one. So let's first of all write what we have: P multiplied with X transpose times Y to the inverse times P transpose and to the whole transpose. So now what we have to do, we have to just reduce this term by successive multiplication. So let's start with the this term because it is easier to start, because we have order of x, so we can write the order. Let's denote order as O. So order of X transpose, so I have to just flip these entries 4 and 3, so I can write like 3 cross 4, and the order of this Y matrix, it is just simply 4 cross 3. So now I have to find the order of the multiplication of this transpose with this one. So now you can easily see that the number of column in this transpose is exactly same as the number of row in this Y matrix. Then and then the multiplication is defined. Here this condition is satisfying. Number of column in the first matrix is exactly identical to the number of row in the second matrix. So now the multiplication is defined. So now what is the resultant order of the matrix after multiplication? So let's write, I can say order of here X transpose time Y, here this O denote the order. So what is the order of matrix after the multiplication of this transpose with matrix Y? It is just simply the these two element. So I can write like 3 cross 3. So now I have to find out the order of this one, but here they have put at the inverse, so I have to find the order of the inverse, but here the matrix is square, so order will remain as it is. So further let's write it here: order of X transpose time Y to the inverse, it is just simply again a 3 cross 3, because here the matrix after multiplication is square matrix. So again the order is same for the inverse. So now I have to multiply this matrix with either this P transpose or P. So let's first of all multiply with P, and now again the order of P again has value of 2 cross 3, and I have to multiply this P with this whole matrix that I have got it from this inverse. So again 3 cross 3. So now I have to find the multiplication of P multiplied with this Q transpose Y to the inverse. So now again you can see the number of column in this matrix P is exactly same as number of row in this matrix. So again the multiplication will define. So now what is the resultant order? So let's write the order of P multiplied with X transpose Y to the inverse. It is just simply the multiplication of these two numbers. In other words, 2 cross 3 is the order of this P multiplied with this bracket. So now we have find out the order of this whole, and now again we have to multiply this matrix with this P transpose. So first of all, let's find the order of P transpose. So I can write order of P transpose. So I have to just flip this number. So it will 3 cross 2, and I have to multiply this matrix with P transpose, but I have to multiply this with at this side. So I can let's add. This matrix will be on the left hand side here, and this will be the right hand side. So I have to find the number of, so the number of column for this left hand matrix is exactly same as the number of row for this right matrix. So you can see the number of column here is 3, and the number of row here is 3. Then the multiplication is defined because we are multiplying in this order. And remember that matrix multiplication is sensitive to this order, either AB or we are multiplying BA. They are not equal in the matrix. It may have happened sometime, but it's not generally the case. So recall that AB is not equal to BA in this matrix world. So now here again this multiplication is defined. So let's write it here. We have to multiply P times X transpose Y to the whole inverse with P transpose. So now the resultant order. So let's write it here. The order of P multiplied with X transpose with Y to the inverse times P transpose. It has value of this 2 rows and 2 column. So from 2 from the here and 2 from here. So I can write 2 cross 2. So now they are asking about the order of this whole transpose. So again it is the square matrix. So now you can take the transpose. It does not make any difference because it is a square matrix. So let's write it quickly here. The order of, we have find out finally. It is our final step to reach the answer. P transpose to the whole transpose. It is nothing but again 2 cross 2. So now look at the option. Option B is the correct order for this whole matrix after some multiplication with inverse and transpose and taking the whole transpose. So I can say the after taking all these things, the resultant matrix has the order of 2 cross 2 and it is a square matrix. Okay, now let's solve question number 8. Question 8 says, for what values of alpha and beta the following simultaneous equation have an infinite number of solutions. Okay, so we have to find the unknown here, which are in terms of alpha and beta. So first of all, let's form the augmented matrix from this system. Let's form an augmented matrix. So here coefficient for this first equation 1 1 1. From this second equation I can write 1 3 3 1 2, and here I have to put the alpha because it is unknown here. So now let's put the vertical line and put 5 here, 9 and beta. So now to find out the find the value of alpha and beta to get the infinite solution, recall the basic concept of simultaneous linear equation. So now if the rank of this coefficient matrix and the rank of augmented matrix are equal, but it less than the number of unknown, here the number of unknown are 3 because we have 3 unknown x, y and z. So I can say the number of unknown is 3. So I can write like this. If the rank of this coefficient matrix, let's call it A is exactly same as the rank of this augmented matrix. So let's denote as like A vertical line B is same and but it less than the value 3, then I got the infinite solution for this system. And what does it mean? This the rank is less than 3. That means this, at least this, from this third 3 row, at least one row is exactly 0 0 in this form, 0 0 0 and 0. Then I am getting the one independent variable, either z in the other word. So now so z is the free variable and z can take any value from a real number, and according to that I can get the value of successing this further variable. So now in this way we are getting the infinite solution, because the here the at least one solution, one variable is free. If this condition going to hold, then the free variable may take any value from the real number. So now what we have to do, we have to reduce this matrix, and we have to we have to choose the value of alpha and beta such that this matrix is rank deficient. In the other word, it may have a deficiency of 1 or 2, but at least the deficiency of 1 is required for the infinite solution. Or in the other word, this matrix has at least nullity of 1, nullity of order 1. These all statements are equal, but the only the words are different, but they are denoting the same things, either the nullity or the rank deficient or the less than the number of this unknown 3 here. They are all the same things. So now what we have to do, we have to perform some row operation to reduce this matrix into echelon form. So here I have to make this entry 0 and this entry 0. So I can just simply do like this: r2 minus r1 will make my new r2, and r3 minus r1 again will make my new row 3. So now let's perform this two row operation, and what we are getting. So first row will remain as it is. Here I have 5. So now here I am getting s0, here 2, 2, and here 4. Now in the third row again 0, 1, 1. Sorry, here it is not 2, it's alpha. So now here I am getting alpha minus 3, because here it's representing alpha, alpha minus 3, and here beta minus 5. So now to further reduce this matrix, what we have to do, we have to make this entry as 0. So let's apply one more row operation. So I can write like this: if I multiply this row with minus 1 half and add in this one, then this entry will be 0. So let's do it here. R3 minus R2 by half will make new row 3. So now after this row operation, what we are getting, this first row again as it is, this second one also remain as it is. Here I am already 0, and again the minus 1 will come from this second row, and already we have plus 1, so this entry will be 0. So now here again the minus 1 will come from here, and here I have alpha minus 3. Sorry, I make mistake here. I am multiplying this with minus 1, so I must got here alpha minus 1, not minus 3. Sorry for that. Here minus 1, because I am multiplying this first row with minus 1, adding in this third one, I have subtracted these 3. Sorry for that. So now what we are getting, we have to subtract again 1 from here. So I can say I am getting alpha minus 2 here, and I have to, here I am getting minus 2, and I have to subtract from this minus 5. So I can write b minus 5 minus 2, so I will make it minus 7. So now we have reduced this matrix. So now if I want to make this third row as whole entry as 0, then and then this condition is going to hold. If I make this element as 0 and this element as 0, then this matrix has two non-zero rows. Then I can say the rank of this coefficient matrix and augmented matrix has 2, and which is less than the number of unknown here, in this case which are 3. So I can say this matrix will be rank deficient for some particular value of alpha and beta, and that I have to find out for what values of alpha and beta this matrix will be a rank deficient. So now let's make this element as 0. So I can equate this alpha minus 2 equal to 0. So I can easily say that the value of alpha here is 2. Not confused with here, it is an alpha, and here in the right on this, here in this place I have to make again 0. So beta minus 7 equal to 0. So again I can say the value of beta will be 7. So now if I put this well, I substitute this unknown with the help of this value. Alpha is 2 and beta is 7. Then this system has an infinite solution. So now the value of they are asking in this order alpha and beta. So I have to write the value of alpha first, which is 2 and 7. So option A is the correct one. Not confused with option B because they are asking in the same order. So we have to write the alpha first and beta later. So alpha has value 2 and beta has 7. But here the option B order is reverse. So do not make mistake here. These all are not correct set of value for alpha and beta. So only option A is the correct one for this question. Now let's move to the question 9. Okay, now let's solve question 9. So question 9 says let A be uh, n cross n real matrix such that S square gives me an identity matrix and Y be an n dimensional vector. Then the linear equation Ax equal to Y here. Again this Ax equal to Y, it is the set of simultaneous equation. Here x is coefficient matrix, sorry, A is coefficient matrix, x is our variable vector, and again Y is n dimensional vector. So now a condition is given about this coefficient matrix. Here it is given that if I square this matrix, then in the output I am getting the identity matrix. So now the four option says A has unique solution, option B says A has no solution, C says more than one but finite finitely many independent solution, and option D says infinitely many independent solution. So now to reach the conclusion about the solution, we must know the condition about this, we must know the determinant of this coefficient matrix. If the determinant of this A will 0, then again the remember two possibility. The one possibility is that either the system has a no solution, so this is the first possibility for the value of determinant is equal to 0, and the second possibility is that uh, if may I got infinite solution. So these are the two possibilities associated with the determinant equal to 0, and if the determinant of coefficient matrix is non-zero, then the only one possibility and system has unique solution. If the determinant is not non-zero, then system has unique solution, because what does it mean that determinant is non-zero? That means all the rows or all the columns of any matrix are linearly independent. Then and then I am getting the determinant as equal to non-zero. That's mean this matrix is not rank deficient, it has a full rank. So now I can say from the basic concept that the rank of this coefficient matrix is exactly same as rank of augmented matrix, and which is exactly the same as number of unknown in this particular case. So the system has a unique solution for this case. So now if first of all I have to find the determinant of this matrix A here, but now here we do not know the any elements of this coefficient matrix. So we have to again here we have to take the help of Cayley-Hamilton theorem, because the equation is given in this form s square equal to I. So again let's use the Cayley-Hamilton theorem to reach the conclusion for this question. So now I can say I can replace this A with lambda square, and here the lambda is eigenvalue. In the reverse, I am using this Cayley-Hamilton theorem in the reverse order, because the Cayley-Hamilton theorem says that every matrix satisfies its own characteristic equation. So now if I replace this A square with lambda square, so I can write like this lambda square equal to I. So now if you I am going in the reverse order, because the Cayley-Hamilton says replace this lambda with matrix A, but here in this case I am replacing this matrix A with eigenvalue lambda. But the theorem is stay must true in this reverse order also. So now let's find the eigenvalue from this equation. So I can say the eigenvalue, I have to reduce this identity matrix as 1, because I am going to the polynomial from this matrix equation. So I have to replace this identity with unity in the polynomial term. So I can write the lambda equal to plus 1 and lambda equal to minus 1. So now let's use further one more important property of eigenvalue, which is the which state that the multiplication of all the eigenvalue for any particular matrix. Here I have 2. It is nothing but the determinant of matrix, and here the matrix is A. So I can write the determinant of matrix is nothing but the multiplication of these two values. So I can say determinant of A, which is minus 1. So I have find out the determinant with the help of this Cayley-Hamilton theorem and the condition given in this question. So now we know that determinant is non-zero, then this possibility is going to happen because the determinant is non-zero, then the system must has a unique solution. So now options A says a unique solution. Yes, option A is the correct statement about this equation in this form, ax equal to y. So now with the help of several property and Cayley-Hamilton theorem, I can reach the conclusion about this system with the help of this equation, this condition. So now let's move to the last question for this video. Okay, now let's solve last question, question number 10. So question 10 says the eigenvalue of a 2 cross 2 matrix X are minus 2 and minus 3. The eigenvalue of matrix X plus identity matrix to the whole inverse multiplied with X plus 5 times identity matrix. So now we have a matrix, given matrix, which is X. So now let's represent this value as lambda 1 and lambda 2 are the eigenvalue of this matrix A X. So I can write here plus 2 and here minus 3. So now they are asking about the eigenvalue of this matrix. So let's write it here also, X plus identity matrix to the whole inverse multiplied with X plus 5 times identity matrix. So now we know the eigenvalue of this matrix X, and we also know the eigenvalue for identity matrix. So again let's write it here. Eigenvalues for identity matrix are 1. All the eigenvalues for this identity matrix of any order, let's call it n cross n, are 1. So now what we have to do, we have to just replace this X with this particular eigenvalue and this I with 1 with the help of Cayley-Hamilton, not Cayley-Hamilton, but it is the basic property of any matrix. If I am performing some if I am making some equation in the form of matrix, then this equation must be satisfied by this eigenvalue. So now what I have to do is just simply let's replace this minus 2 first with this X with minus 2. So I can write here minus 2 plus this I with 1 to the minus 1, and here this X will minus 2 and here plus 5. Now here it will become a scalar. So now minus 1 to the power minus 1, and again here plus 3. So now here the inverse of minus 1, but here minus 1 is just simply scalar. So in the same way I can write like 3 like this, because the negative power will come in the denominator. Here it will no longer any matrix. So I have not need to find the, even I cannot find any inverse, because here it is a matrix. So we can call it an inverse of matrix, and here it is just scalar. So I have to bring it in the denominator. So it's give simply just minus 3. So now one of the eigenvalue for this matrix is minus 3. So now option C and D will cancel out. So now let's check for this minus 3. Again replace this X with minus 3 in this equation. So let's do it here. So minus 3 plus replace this identity matrix with 1 to the inverse, and here again minus 3 plus 5. So now here again I can write as minus 2 to the inverse, and here positive 2. So now here again I can take this term in the denominator. So I can write like this, 2 by minus 2, and which is simplified as minus 1. So now the second eigenvalue is minus 1. So now the correct set of eigenvalue it is present in the option A. Option B has the second eigenvalue is negative 4, but we are getting minus 1. So again option B is wrong. So only option A is the correct set of eigenvalue. So now you have to remember this property, because if I am making some in some form of any form of equation with the help of matrix, then the eigenvalue of this any matrix, let's call it matrix M, it is just simply we have to put the eigenvalue of this matrix here and 1 at the place of identity matrix, and it will give me the eigenvalue of this matrix M. Now in the same way I can also form the equation like this: x to the 5 plus 3 x to the cube and 3x plus I. So now if someone asks the eigenvalue of this matrix M, so we do not have to find the matrix M with the help of this raising the power of this matrix to the 5 and 3 and then multiplying and simplifying. We just what we have to do, we have to just find the eigenvalue of this x, and we have to put here at the place of x, and we have to perform some we have to make this power 5 here and power 3, and so simply multiply here with 3, and we have to do some algebraic addition and subtraction. Then I am getting the eigenvalue for this matrix A with the help of property of the eigenvalue. And that's it, and thank you for your support, and keep supporting this channel. Thanks for watching this video. See you later in the next video. Take care of yourself. Bye bye.